Now, one thing that was mentioned was alcohol oxidation. The reason I didn't write that up is because that we're going to talk about as part of this chapter. Generally, because understanding alcohol oxidation requires some understanding of carbonyl chemistry, they don't talk about the mechanism for that in the alcohol chapter. They save it for now. I'm not sure exactly what Klein does with it. He may put it in both places, but we have to talk a little bit about what happens with carbonyl groups before we can explain why certain things will and will not occur. We'll take the easy one first. What happens if I start from a secondary alcohol and I oxidize it with something? What do I get? I get a ketone. What's the something? PCC is one option. Or you can actually get away with chromic acid as well. It wouldn't matter, since there's no possibility of overoxidation. What about a tertiary alcohol? What happens if I try to oxidize that? What? Doesn't oxidize. Oxidation has a couple of different definitions. One, forming more bonds to an electronegative element. Two, forming more bonds to oxygen. Three, forming less bonds to hydrogen. This version, the formal oxidation of an alcohol, requires both. To form a second bond to oxygen, we have to unform a bond to hydrogen. This doesn't have one. So, it does not oxidize. Okay, now the tricky one. Primary alcohol. Depends on what you use. If I use chromic acid, chromium trioxide, and sulfuric acid, I get overoxidation to the carboxylic acid. Not entirely satisfactory to me if I wanted the aldehyde. I can't stop it. If, on the other hand, I alter the chromium reagent slightly, I can stop it. Why? This is why it's not in the alcohol chapter, because you need to know a little something about carbonyls first. Okay. Let's talk about the reagents. Chromium trioxide, present in both, usually drawn like this, although it can be drawn with resonance form, sometimes drawn protonated in the top case. PCC still has chromium trioxide. So the oxidant is actually the same, but it has a different acid. The P, pyridinium, an aromatic pyridine, protonated. The other C, a chloride, is made from the hydrochloride salt. And the second C is the chromate, pyridinium chlorochromate. Okay. There's also pyridinium dichromate, which has the pyridinium ion and a Cr2O7 instead of the CrO3. Reaction is exactly the same. PDC is a little bit easier to handle, but that's not really relevant right now. Okay. So why, if we're using acidic conditions with the same oxidant, are we seeing different products? Why is that possible here? regardless of which one we actually use, I'm going to make this a little bit more generic because it applies to essentially any primary alcohol, not just the one I was showing. If I take chromium trioxide, generally speaking in an acid medium, sulfuric acid preferred, but we'll just take a generic acid for right now since we're talking about the generic first step. What I'll get is this, and I can draw that as a resonance form like so to explain why it is that it's relatively easy for an alcohol, which is not a very good nucleophile in general terms, to attack. It may not require protonation first since this is a metal, but here we are. Like so. And generally speaking, probably another chromium trioxide, but possibly something else depending on the reaction, will take the job of getting rid of that. Which puts us here. Now what? Well, now we actually have something else acting as a base, causing an elimination. Because this is a metal, its oxidation state can change, therefore, it can actually take those electrons directly without having any other consequence. And where do we get? Aldehyde. This is common to both reactions. And we're left with a chromium species at a different oxidation state. So it is not recyclable. Okay. So why does one stop at the aldehyde and the other continue, even though the oxidant is the same? And this does not have anything to do with how much you use. It is not a stoichiometry question. If it were, you wouldn't need PDC. You would just measure out the chromium trioxide more carefully to begin with. That's not how it works. How do I get it under control? To explain what happens next, we actually have to think a little bit about the medium. And that is what's actually present in the flask. I know, big concept for chemistry, right? Let's think about what's in the flask. However, if you just look at the conditions and don't think about what that actually means, you will never be able to explain what actually happens here. Well, chromium trioxide is an orange solid. Sulfuric acid is a viscous clear liquid. And your alcohol goes in place, and that's it. Sort of. Sulfuric acid, if you read the bottle, concentrated form, will we'll say something like this. I think it's 98 or 99. 99% by volume sulfuric acid. So, all obvious political jokes aside, what's the other 1%? And it does matter. Because it's at the core of this. What? Water. Aha. So in our over-oxidation, the one that has sulfuric acid, I also have this present. Why does that matter? No. Well, technically yes, but there's a little more to it than that. Why does it matter that water is there? Because water is a reasonably decent nucleophile. After I form the aldehyde, that's right. After I form the aldehyde, I still have acid present. In this case, it's sulfuric acid, which means that mechanism I had up at the start for protonation, followed by relatively weak nucleophiles attacking, might be important here. It's all reversible, as are most of these, to a point. This is the aldehyde hydrate. Net addition of H and OH across an aldehyde pi bond. It lacks a pi bond. It is tetrahedral. In some cases, they are isolable and relatively stable. But in the process of losing that double bond to oxygen, what did I gain? In functional group terms, I went from a carbonyl pi-bonded oxygen to what? I went from an aldehyde to a what? To a diol. We don't really care about the di part, but I went from an aldehyde to an alcohol. Newsflash, chromium trioxide reacts with alcohols. So, we end up losing that H and getting to this. So, yes, it is responsible for the oxygen that you need to make the carboxylic acid eventually. This is why you can't stop chromium trioxide with sulfuric acid, because you can't get sulfuric acid without water in it. Nor can you get any of the other strong inorganic acids without water in them. Hydrochloric acid, 63% water. Nitric acid, 45% water. HBr, 55% water, I think. That one I'm not sure of. Phosphoric, I think, tops out at like 15% water. So, you must think sometimes about what else is present, even if it's not an intentional reagent, especially if you see something odd occurring, like a reaction that continues when you didn't want it to. Why would that happen? Chromium trioxide does not react with aldehydes. Period. It does react with diols, regardless of their source. So, if you have an aqueous acid, then you will have a concentration of the diol. It may not be a lot, but remember Le Chatelier's principle. This goes on to the acid, so it drops this concentration effectively to zero. What happens here? We drive towards that. That's why you can't stop it. Even though that hydrate is not particularly favorable, it does undergo a reaction that's not reversible. When that happens, its concentration drops to zero. Le Chatelier's goes towards forming more of it. Okay. So, with that said, how does PCC work? More precisely, let's add some detail to it. PCC, pyridinium chlorochromate, is used in dichloromethane, typically as a solvent. PCC, because your acid is the salt of an organic base, PCC is a solid. Solids can be dried, which this is. So can solvents, which this is. Dichloromethane can be distilled. PCC can be desiccated. And so the one thing you will not have in the lower reaction is water. You don't have water, you don't have a hydrate. You don't have a hydrate, you don't have an alcohol beyond the point where the aldehyde forms, which means you don't have a second reaction. If you're sloppy and don't dry your solvents, if you leave the bottle open on the PCC and let it absorb water from the air, then you might have a problem. PCC is also, pyridinium chloride, the acid as part of that complex, is not nearly as strong of an acid. So it's very likely that it will not actually do the job of protonating the aldehyde. So it probably is selectively reactive as well. But the big point is it rigorously excludes water. And water is the culprit for why this reaction over-oxidizes in the first case. Now, that's a bit of an experimental problem. In a lab, in a paper setting, you wouldn't be thinking like that, but you have to kind of do that sometimes. The one thing that you're going to learn in this course, as we do a lot of reactions with aldehydes, ketones, esters, acid chlorides, and beyond, is that water is generally not your chemical friend. It may be required for you to live, but in your reaction, it will generally screw you every time. Water is relatively acidic compared to most of our nucleophiles. Water hydrogen bonds to things. Water interferes with a lot of things that we would prefer it did not. And this is one of them. We don't want it around. Okay, so we keep it out. Easy enough.